Thank you, Fang. Our next speaker is Ima, a computer vision expert who recently joined Microsoft Research Asia and leads the computer vision group at Microsoft Research Asia. Prior to joining Microsoft Research, he was a tenured professor at University of Illinois, Urbana-Champaign. Today, he will give us his talk on how we can rectify everything we see. Let's give a warm welcome to Ima.
Okay, good. Yeah, thanks everyone. So I'm Ima. Actually, I'm the manager of the computer vision group. So you know that what computer vision do, we actually just move around pixels. So today you will see a lot of videos showing how we move around pixels. And this is actually some of the recent work. Actually, the work under the title Tilt is the work I did in the past couple of years precisely at Microsoft Research Asia. Actually provided good environment for me to really substantiate some of the ideas that we had back in the cornfield in Illinois and actually show some of the good applications. So the world is full of regular objects, right? We're interested. Textures, buildings, faces, license plates, barcode, or all kinds of texts, right? So there's something interesting about those objects or those images, that their images actually in the upright position, they actually exhibit some interesting properties. They're actually low-dimensional structures. We all recognize the upfront position of text or human faces. Why is that? Right? What's special about this particular pose? Right? So, well, maybe you can say there's a lot of local regularities, global symmetries, right? So then how can we utilize those for our purposes? Right? Especially provide natural user interfaces. We want to recognize barcode with our cell phone, or Google Goggle has advocated ideas of recognizing any landmarks in the world using just a camera. And also WordLens can instantaneously translate English to Spanish and vice versa. Can we do this? Right. But why we have not yet had those gadgets yet? Because the objects we see through a camera are distorted, deformed, right? You can take a picture from an arbitrary angle. The images, this upright image can be distorted by maybe just your view angle, or maybe distortion by the curved surface, or can be occluded by a tree, or could be, have a severe distortion introduced by the camera we'll see later. So this is actually present a very fundamental technological challenge. Can we recognize object despite the deformation? Right? Why our human beings can do it very quickly, very efficiently? Then, hence the title, how can we rectify those objects? So there has been a very, very challenging problem. It turns out actually recently, in the past couple of years or few years, there has been some fundamental mathematical breakthrough that provided us unprecedented, efficient, and powerful computation tools. Right? Allow us actually to recover such important structures in the signals and images, despite you have severely undersampled measurements, or errors, gross errors, such as occlusions or corruptions, and despite huge domain transformations. And we'll see quite a few examples what kind of deformation we can already handle, potentially suggest that more things will come. Right? Obviously, the first deformation mostly we see is through your view angles. Right? You would like to recognize this building, hopefully from the frontal view. And depending on where you take the picture, the facade of the building will be severely distorted. Probably very few of us have ever seen that the Empire State Building from this particular angle, right? So this kind of techniques allows you to correct this kind of strong perspective distortion. What it enables us to do? Enables us to reconstruct large-scale buildings, 3D models, full 3D models, including camera positions from a few set of photos. Right? This has been a very, very challenging problem, has been tackled by computer vision in the past 20 or 30 years. Right? So far, I think we are about to develop very efficient tools, allow us people to do this very, very efficiently now in the future. And also, other factors also introduce deformation, such as your lens. You have a bad lens, for example, fisheye lens, right? So you take a picture and things will get severely distorted. And you don't have to worry anymore. You just have to point your camera to anything that is sort of irregular, and then the computer can automatically recover. So stratify, make all the straight lines straight. No longer looks like a fisheye, and it will be like a standard camera. Right? This can be done automatically without any human interactions, actually, at this point. Why this is useful? Because, well, we're selling a lot of cheap cameras, right? The Kinect actually is a very, very affordable camera. But one of the challenges is that the lens associated with Kinect camera has severe distortions. Especially nowadays, we're using camera no longer as a teleconference, as a monitor. We're actually using it as the interface between human and computer, right? For that purpose, you have to calibrate it, right? So the old technology of calibrating camera takes painfully a lot of time, but also it's not accurate. But recently, we're actually using some of the new techniques we're developing at the MSRA, and we can just do this in a matter of seconds, fully automatically, without any human interaction. So you just have to point your cameras to a few patterns, and you're done. You get a perfect calibration, despite the severe distortions and the perspective or intrinsic parameters and extrinsics. Right? In fact, the 5 minutes is a really exaggeration of the performance of the current toolbox. Anyone who has played with calibration, you know it sometimes takes up to an hour. Still get a wrong answer with calibration. Right? Also, the object in the scene also could present certain types of deformation, right? The curved surface like this. Now, unless you really can recover the 3D shape and also the camera pose, you will be able to recover what's truly the intrinsic upfront pattern, right? So this is an example of Temple of Heaven, but with a simple initializing, as you can see, the pixel gets moved around according to the intrinsic structure. By the way, this technique actually involves, it's truly very interesting because it only deals with the raw pixels without any low-level image processing, filtering, or feature extraction. We just deal with the raw data automatically and get what you see is almost what you get. What you get is what you see, almost, right? And what is this useful? As I mentioned earlier, you have a cell phone, want to recognize text, but unfortunately, you cannot stay inside the traffic to take a picture of the sign you're interested, right? If you want to. So normally the angle you took is from this angle, a very oblique angle. But the current OCR cannot handle this kind of deformation. So what you can do, you can detect the text, rectify it, and send to the OCR. So as you can see, some of the demos showing that process. And we elaborate what is detection, rectification, and recognition. And there's also a comparison between if you don't do the rectification, what would happen to the current OCR technology. Right? So actually, the comparison is pretty drastic. So unless you can really rectify the things, then the system will be able to recognize. Right? This is some of the things we're also hoping that help with Be Mobile in the future. And as we say, it rectifies all types of text: a barcode, license plates, Chinese, English, right? Without exception. Actually works remarkably well. And also rectify many types of objects. Right? Anything with some kind of regularity or symmetry. Right, butterflies, faces, lips, and so on. They have this nominal position. This kind of tools can help you to find it automatically, and hence you can use it for everything, right? So, at one of the most popular blog at Computer Sensing, recently, actually just last week, they had a blog about our techniques, both of cities and also calibrate cameras. We can sell millions and billions of cameras, very cheap, despite their low quality. We can rectify them. And also, we can rectify and recognize text. We can do translation, speech synthesis, and integrate all the rest of the products that have been developed at Microsoft Research Asia and Microsoft Research in general. And hopefully, these techniques will apply to many other objects that we're interested in: faces, signs, license plates, and so on. And will make the computer a much better, provide a much better natural user interface for the computers in the future, and make them much more intelligent when they're interacting with us and also with the real world. That's my talk. Thanks.